Welcome to This Explainer. We're jumping right into a highly detailed cinematic journey deep into the modern engine management system. We're talking 3D cross-sections, glowing electrons, the whole shebang. We're stripping away the grease and the heavy metal to look at the incredibly high-stakes, high-tech digital world operating completely unseen under your hood. As one master mechanic in our sources put it beautifully, today we're diving deep into the electrical pulse of the modern engine management system, right down to the skeleton. And that's exactly what we're doing, because beneath all that heavy, vibrating iron of a diesel engine lies a fragile, microscopic world of precise electronics. We are looking at a system where heavy mechanical rotation meets absolute digital perfection. So what exactly is the Hall effect? And how does this microscopic phenomenon actually power a massive modern engine? Let's zoom in from the macro level of the engine block right down to the atomic level to find out. Believe it or not, the underlying physics here aren't actually new. Way back in 1879, a physicist named Edwin Hall stumbled upon this effect. Fast forward to today, and his 19th century discovery is absolutely critical to modern vehicles. You'll find it everywhere. Wheel speed sensors, camshaft sensors, and for sure, the star of our explainer today, the crankshaft position sensor. Section 1. Inside the Hall effect. Picture a thin, highly conductive semiconductor crystal. We pass a constant electrical current right through it. Now, if you introduce a magnetic field at a right angle to that crystal, this fascinating physical reaction kicks in, called the Lorentz force. It literally shoves the glowing charge carriers, the electrons, to one side of the plate, and pushes the positive poles to the other. If you measure across those two sides, bam, you get a voltage. But here's the catch. It is an incredibly weak, raw, analog voltage. We're talking just a few millivolts here. Which brings us to a crucial problem. Your engine control unit, the ECU, is a digital computer. It needs absolute, black and white certainty. So how on earth does an ECU run off a fluctuating, incredibly weak physical reaction of just a few millivolts? The answer is a tiny piece of integrated magic called a Schmitt trigger. Built right into the sensor head, this thing acts as an internal digital switch. It takes that weak, wavy analog voltage and instantly snaps it into a sharp, clean digital signal. It's like a light switch that absolutely cannot get stuck halfway. The output is strictly 100% on or 100% off. It literally transforms a physical wave into a bright, perfect digital square wave. When we stack this up against older tech, you really see why this is a total game changer. Older inductive sensors were simple, just a 2-wire coil and a magnet, but they output an analog sine wave. Crucially, at low cranking speeds, an inductive sensor's voltage just drops heavily, making it super hard for the ECU to read. A Hall effect setup needs 3 wires because of that extra power feed. But the massive advantage is its low-speed reading. It is absolutely flawless. Because it's a digital switch, that digital square wave amplitude stays perfectly constant, whether you are barely cranking at 200 RPM or screaming at redline. Section 2. Synchronizing the engine. All right, let's zoom back out to the heavy metal. The Hall sensor sits perfectly stationary on the engine block, staring right at a rotating target called a reluctor wheel that's attached to the crankshaft. As this metallic, teethed wheel spins rapidly, every time a metal tooth passes our sensor, the magnetic field concentrates and the Schmitt trigger snaps on. When a gap aligns, the field weakens and it snaps off. Tooth by tooth, it creates this continuous, beautiful sequence of square waves. But hold on, this introduces a pretty big logical problem. Sure, by counting the time between these square waves, the ECU can easily figure out the engine speed or RPM. But if every single tooth on that spinning wheel is identical, the signal is just an endless repetitive loop. So how does the ECU know the exact rotational angle of the crankshaft at any given millisecond? The engineers solved this one brilliantly. Identical teeth only give you RPM. But to get an exact angle, they intentionally break the pattern by just removing one or more teeth from the reluctor wheel. When this larger, missing tooth gap flies past the sensor, the ECU detects a longer interruption in that crisp square wave signal. This gives it a totally unambiguous angular reference point. Now it knows exactly where the crankshaft is, and it starts counting the standard teeth from that specific point to reconstruct the precise angle. However, even knowing the exact angle of the crankshaft isn't quite enough. In a modern 4-stroke engine, a piston reaches top dead center twice per cycle, once on the compression stroke and once on the exhaust stroke. The crankshaft actually spins twice for every full engine cycle. That means the crankshaft sensor signal is totally identical for both of those rotations. It literally has no way to tell if the cylinder is ready for fuel, or if it's just pushing out exhaust gas. And this is exactly why the camshaft position sensor, or CMP, is so vital. Usually, this is another Hall effect sensor, but it watches a target wheel on the camshaft, which spins at exactly half the speed of the crank. The ECU takes the digital square wave from the crankshaft, overlays it with the digital square wave from the camshaft, and instantly knows exactly which stroke each cylinder is on. This perfect synchronization is the whole secret. It's what allows the ECU to confidently fire the fuel injectors and spark at the exact right millisecond. Section 3. Diagnosing the skeleton. The Nissan YD25. Let's bring this theory into a real-world workshop scenario. We're looking at a Nissan NP300 with a YD25 turbo diesel. Anyone who's wrenched on high-mileage engines dreads seeing this specific sequence pop up on a scanner, P0335 or its cousin, P0340. It is the universal code for a massive headache, usually leaving you with an engine that just cranks and cranks but absolutely refuses to start. According to the master mechanics in our sources, this is the classic YD25 timing issue. Remember how the ECU relies on the rising and falling edges of those crisp digital square waves aligning perfectly? Well, over thousands of miles, the heavy primary timing chain on that engine physically stretches. Here's the crazy part. The Hall effect sensors are actually doing their job perfectly. They are sending pristine signals. But because the chain is stretched, the camshaft square wave shifts slightly out of phase with the crankshaft square wave. The ECU sees this electrical misalignment, assumes the timing is jumped, and immediately cuts fuel to prevent catastrophic engine damage. So this begs the question, if you're actually diagnosing this exact crank no start condition on an NP300, how do you test this Hall sensor to know if the sensor itself is dead or if that timing chain is just stretched? You definitely can't just guess. You really have to diagnose this at the skeleton level. Step 1. Check the harness. Unplug the sensor, turn the ignition on, and grab your multimeter. You absolutely must have your 5-volt reference and a solid ground. If you don't, hey, you have a wiring issue, not a sensor issue. Step 2, if power and ground are solid, plug it back in, back probe that third signal wire, hook up an oscilloscope, and crank the engine. Step 3, analyze the waveform that pops up on the screen. Now, when you analyze that waveform on the oscilloscope, you want to see a perfectly crisp, bright green, digital square wave instantly pulsing between 0 and 5 volts. If that internal Schmidt trigger chip is failing, the scope will not lie to you. You're going to see rounded off waves, maybe stuck constant voltages, or just messy, irregular dropouts. That right there is when you know the digital electronics have failed and you need to drop in a new sensor. As the expert engineer in our explainer so perfectly puts it, always trust your oscilloscope. When you're dealing with components that turn invisible magnetic fields into a digital pulse, you literally cannot rely on guesswork. You have to rely on precise electrical diagnostics. Which leaves us with something pretty wild to think about. We've just seen how a 19th century physics discovery is currently managing the violent, heavy mechanical forces of a modern engine block with microscopic 5-volt precision. But as our vehicles push for even tighter emissions and higher performance, they are becoming entirely reliant on this flawless digital data. So what happens when the inevitable, heavy mechanical wear of the next generation of engines begins to outpace the delicate tolerances of our digital sensors? It's a fascinating collision of heavy iron and digital code, and you know what? It's only going to get more complex.